this question, we have a set of capacitors and resistors arranged in a circuit. We have an ammeter connected in the circuit. It says that the ammeter is idealized. That means we're assuming that the internal resistance of the ammeter is 0, so it doesn't contribute to changing the current in the problem. The battery has no internal resistance, so that's a perfect battery. It supplies 100 volts of potential. And we want to find the reading of the ammeter just after the switch is closed and after it's been closed for a long time. Okay, so let's start with part A. What does the ammeter read? What is the current in this branch as soon as that switch is closed? So let's start by quickly re-sketching our circuit. We've got our 100 volt battery right here. We've got our switch. We've closed the switch now. We've got our ammeter. We go to the 15 ohm resistor, then up here we've got our 15 microfarad capacitor. Attached to a 25 ohm resistor, those two guys are in parallel. We've got a 75 ohm resistor, 20 microfarad capacitor, 50 ohm resistor, 25 ohm resistor, another 25, and then in parallel with that resistor, we've got a 10 microfarad capacitor. Okay, so part A says that just after the switch is closed. So let's ask, what does that mean? So what happens when you have a capacitor in a circuit with a battery is that as soon as we close the switch, as soon as it starts to charge, the capacitor is very easy to charge. It accepts lots of charge. There's no repulsion by other charges on the plate. So as soon as the switch turns and connects the circuit, the capacitor can charge very, very efficiently. What does that mean in terms of our circuit? So we get a current that comes out. We get a current that comes out here. There's the current that comes out of the battery. It has two choices. It can either go up through the 25 ohm resistor, or it can go through the capacitor, which is easy to charge. This prevents no obstacle to the flow, so all of the current is going to go through this one. That means that as soon as the switch is thrown, the capacitor acts like a short circuit. So what that means is that it acts like a piece of wire. So what that means is that all charge flows through the capacitor and none flows through any resistor which is in parallel. So in terms of our circuit here, what we have is that this resistor will draw no current because all of the current will come through here. These two guys are in parallel, so this resistor will draw no current. It all goes through there. So then let's ask, what does the current flow look like in our circuit? So let's get that on our picture as well. So the current is going to come out through the battery. So it comes out here, goes through here, comes through the capacitor, then passes through this resistor. It has no choice, it has to go through this one. So it comes this way, it hits a junction right here, and there it has two choices. Let's draw these guys in different colors so they're a bit easier to see. For one choice, it can come straight down through this branch, through the capacitor, and then through the resistor. So that's one thing that can happen. For another choice, I'll grab my blue pen. For another choice, it can go through here. It won't come down here because it has a choice between capacitor and resistor. Capacitor is easy, so it'll come down through here and around like this. So that's what the currents are going to do in this problem. Let's redraw our circuit, taking out those resistors so it'll be a little bit easier to see as we work through it. So we'll redraw. So there's our circuit, and we said our capacitors act like short circuits. So it means it's easy to flow through. So we'll redraw once more. So now our circuit looks like this. Okay, so this circuit, as soon as the switch is flipped, the current starts to flow, charge starts to flow, none goes through the resistor, it all goes through here, no impedance to flow, so it's like that capacitor is just a piece of wire, that resistor is not there. So we next come to the 75 ohm resistor. Then the current gets to this point, it can branch, part of it comes down through here, this acts like a short circuit, we replace it by a piece of wire, then it goes through the 50 ohm resistor. Some of this current also goes through this branch. It picks the capacitor over the resistor because it's like a short circuit, so that is gone, and we're left with this 25 ohm resistor. And then down here in the bottom we have the 15 ohm resistor. So now this is something we can deal with. If we want the current through the ammeter, we have to find the current that gets put out by the battery. So we want to find this current. We can do this, we can either use Kirchhoff's potential and current laws, or we can solve using equivalent circuits. Why don't we do this one using equivalent circuits? So let's start to draw an equivalent circuit for what we have here. The 50 and the 25 are in parallel. If they're in parallel, then what that means is we can add those up and find an equivalent. Our parallel equivalent says 1 over R equivalent equals 1 over 50 ohms plus 1 over 25 ohms. 1 over 50 plus 2 over 50 is 3 over 50. So our equivalent in this step is 50 over 3 ohms. You can do that in numbers, or you can just leave it as 50 over 3. That gives us an equivalent circuit that looks like this. So we've got the 75 up here. We've got our equivalent right here. We've got our 15 down here, and our ammeter in series right here. These guys are connected in series. To get a series equivalent, we just add them up. When we add those up, what we get is 106.7. If you want to put out a number, if you wish, you can leave it in fractions. That would be fine too. So our final equivalent circuit has our 100-volt battery in series with a 106.7 ohm resistor and an ammeter. So the current that the ammeter will read is the current that flows through this circuit I. We can use our Ohm's law. Ohm's law says that the potential equals I times the resistance. So our current I is the potential divided by the resistance. Potential is 100 volts. Resistance is 106.7 ohms. So we get a current going through that circuit of 0.938 amps. So that's the ammeter reading as soon as the switch is closed. In the next part, we'll find the ammeter reading after it's been closed for a long time.